So first of all, we view it as a problem of optimization with multiple objectives. So at least two objectives, reducing emissions or environmental objectives, and well-being. The previous lecture, by the way, is mentioned the money metric utility, which is exactly what we do, how we measure well-being. But there are all kinds of constraints, of course, and this optimization is not a simple optimization. There's always a budget constraint, there are public opinion that we need to deal with, and there are other context-specific constraints, such as the physics of the problem. And then there are actions or solution. I will use the word actions and solution interchangeably. Things like pricing, incentives, regulations, taxation, technology development, and information. So it was mentioned also earlier today that the actions or the solutions can be demand-oriented or supply-oriented, but whether it is demand-oriented or supply-oriented, to predict the outcomes in terms of emissions or well-being, we need both demand and supply. And the demand model, the demand part, is where the behavioral models are. How do the agents that are relevant, people, households, sometimes business establishments, how do they respond to these actions? And so the modeling or the study of behavior that we are engaged in is in specifying this demand model. And so I mentioned here some examples of things that are choices that will be in the demand part, like technology adoptions, choices that people make about their activities, and on the supply side, mobility and energy systems that can be affected by the kind of solutions that we talk about. Then the demand and supply are nowadays, people say that we can use machine learning. We don't. Machine learning requires that you have data in which the kind of action or solutions already have been implemented and are usually not. So in the data that we have, we do not observe the impacts or the response to by human to the kind of actions that we are interested in designing and predicting the consequences. So that's why we use behavioral models we rely on experimental data or natural experiments or whatever data we can get, but behavioral models as opposed to just relying on correlations. So predictions of impacts cannot be exclusively data-driven, meaning machine learning, but requires modeling and simulation experiments. And so that's the idea. The idea is that we need to have some sort of a laboratory, which is a simulation laboratory, to which we can bring in the different actions and, of course, develop scenarios about possible futures and predict the impacts. So this is like the analytical framework. And next I want to talk about smart solution. There are solutions, there are actions. What makes them smart or intelligent sometimes? So there are three elements that we are relying on: prediction, optimization, and personalization. So prediction and optimization are kind of obvious that we're not talking necessarily about long-term prediction, but we're talking also about short-term prediction, because if you're trying to predict how humans are going to respond to different actions. It's not happening in the past, it's happening in the future. So that's prediction. Optimization is obvious, it's an efficient use of resources. But personalization nowadays, we have a lot of information about individuals. There is a great deal of heterogeneity in terms of behavior. So why should the solution be unique? Why should the solution be uniform? So even the solution can have individual specific aspect to it. So that's the idea. The idea is that whatever solution we are going to work on, we think about, can we have a customized solution, or take the solution, develop a customized treatment for an individual, given what we know about that individual. And there's a lot of personalization going on. Everybody that is getting on the web or any kind of mobile application is getting a personalized treatment. And so we had to come up with a name for this framework of prediction, optimization, personalization, POP. And so we were inspired by other pop, like J-pop, K-pop, and so we call it Thai-pop. And we also have a diagram for that shows that first of all, that the optimization is done at two levels. So we have here a user or a consumer that is engaged in some activity or some purchase or a mobility activity, for example, and this person communicates with the system using a mobile device of some sort, or maybe it can be an electronic display board, and then the recommendations or the option presented to this individual, or the price, or the discount, or the incentive is based with a back-end system, which we call here a user level. So the user device communicates with a back-end system that develop a solution for that specific individual. But the system itself, we want to optimize it, so we call it the system level. So for example, if we want to provide incentives to individuals, and the incentives are based on the policy, are based on the budget, so this is called the policy. So at the system level, we have an optimization model that will decide on the overall policy, the overall budget. Then given the policy and the budget, when a user wants to participate in this activity, then the user level apply the policy to the specific situation of that individual. So that's the idea. It's called bi-level optimization, where when we optimize at the system level, we take into account what individuals are expected to do at the user level, but we come up with a policy, and then every time a user is using the system, it is presented with an option based on the policy. The policy, this system can work in real time, like for example, incentives today may not be the same as incentives tomorrow. The budget today may be different from tomorrow. The system situation may be different. So the system level optimized periodically, and the user level the optimization is as relevant when an individual is communicating to the system. So the optimization is prediction at the system level, is prediction-based. This is system optimization, the usual kind of optimization that we have in mind, like for pricing, determining the optimal price. But it's an optimal price, maybe average price, or optimal price tariff, but then the exercise of the tariff is the policy. Or the tariff is a policy, and it is applied at the individual level, user optimization. When users behave, we collect information. So the idea is that every time users make choice, we have additional information that allow us to better understand their preferences, estimate their utilities, their money metric utility, so we understand what is benefits to the user, and this information also is fed back to the system level. So that's the idea of a paradigm that we call tripop, that we say this does not necessarily only apply to mobility, to any time we have an application where we have this user and system level, we can apply this idea. Now, we also need a laboratory to test the smart solutions. So for mobility, we developed a laboratory we call C-Mobility. I'm not going to get into the detail, but the kind of results that I will show you in the next section are based on running this laboratory. So this replaced reality, and we program into this simulation the behavioral model, how the user behaves. So we have different agents, and then we have the solution that we are testing, like the incentive system is also programmed, the logic of the incentive system, and then we observe the outcome. So incentives will be the first example that I'm going to explain, to demonstrate to you. So the idea of the incentive is that we have a budget that we can offer individuals to nudge them or to convince them to select ways of traveling that are sustainable. Our system-level objective function here was energy. We want to minimize energy consumption by commuters traveling to work. But for any other trips, it doesn't really apply only to commuters, but there's a budget that is available. And the general experience with incentives is that if you use this incentive budget, which tend to be small, and you apply it in a more uniform, without discriminating sufficiently, it has very little effect. And so incentives have developed, at least in the transportation field, have developed kind of bad reputation as just a waste of money. It doesn't really change behavior. So if you want to nudge people toward a sustainable behavior, we developed here an approach based on tripop, in which the incentives are based on some system-level optimization, but are then personalized to an individual. So an individual is given incentives if we predict that it will have an effect in terms of saving energy. And we allocate the incentive money that we have in an optimized way such that we get an impact. So that's the idea. The idea is that a user has in this case, a smartphone. They are going to make a trip. They ask for recommendation. They get recommendation with, we call it tokens here, but like essentially a payment in kind or an actual payment for different options. Some options do not have any monetary incentive, some options do. And then the person declares what they're going to do. They are being tracked, and if they save energy relative to what they were expected to do without the incentives, then they receive the monetary incentive. It is deposited in their account. So that's the application of this bi-level optimization framework. At a system level, the objective is to minimize system-wide energy consumption, given a total budget available for incentives. The incentives are the budget is then used. The policy level that is based on the system optimization is how much energy we expect per token or per dollar. And that's the way the incentives are allocated and at the user level. And the user is provided with options, included the incentives in a way that maximize their utility, or it's called here the hit rate. The idea is that we want to provide users that will be selected. So the system or the backend at the user level, based on previous behavior, we know the user's utility function. We have a model that predicts what the user will do with the incentive and without the incentives. So we provide the incentive to save energy based on the policy. And so this is a result of simulation. We simulated the behavior of, in this case, 100,000 commuters in Boston. And what we show here that by the budget that is shown in these results is 10 cents per user. So the horizontal axis is the penetration of the app. So the idea here that we have 100,000 commuters, maybe not all of them will subscribe to the service. So the horizontal axis is from 0 to 100. 100 means everyone is using the app. And the vertical axis is a reduction in energy consumption on one side, and on the other side, on the left, on the right, it's the number of tokens that are being used. And so the budget, as the penetration increase from left to right, the total budget spend is spent. So at the 100% level of penetration, the total budget is $10,000 every day. And you can see from here that there is a significant savings. So using 10 cents per user, we get savings which can be as high as 15% or so in energy consumption, which is significant. Whereas if you distributed these budgets almost uniformly, the effect will practically be zero. So that's the first application. The second application is congestion pricing. And so this type of process, this personalization, is useful because congestion pricing, there's a lot of objection to congestion pricing because there are always losers. Every time, every pricing solution with clearly heterogeneous population, there will be losers and there will be winners. And so there will always be objection because there will be losers. So the question is, how can we make the policy such that it is attractive for everyone? So how can we make it to be Pareto improving? And so the idea is that by personalized refunding, not just refunding in general, but refunding which is customized to each individual, we show here in this simulation that we can make everyone better off, even though it is a pricing solution. So the uniform dividends or redistribution of revenue is not guaranteed to be Pareto improving wherever there is heterogeneity. And in most application of behavioral models, there is a great deal of heterogeneity. If you are comparing things like willingness to pay, and the distribution of willingness to pay is huge. And like the variance is often greater than the mean. I mean, the standard deviation, I meant. So that's what we've done here. We show that it's possible to use behavioral model to design a Pareto improving personalized refunding. So the price is the same for everyone. And we also had another application where we talked about discounts. And so there are different ways of doing it. Actually, there are two solutions that are described in this simulation. One is just the fixed price for everyone, or, well, the price change in response to traffic conditions, but there is a refund or dividend. And another approach is called the tradable mobility credit, which is kind of cap and trade, essentially. So the personalization is in terms of the dividends, and or in the case of pricing, in the case of tradable mobility credits or cap and trade, the allocation of credits is personalized. And so the system level objective is social welfare. The policies are, in this case, is the pricing level, the tariff, or how it changes as a function of traffic, and the refunding policy. And because it can be different refunding policies, as I'll explain in a moment. Excuse me. And there are constraints. The constraints are things like human factors, because we cannot change the price too frequent. The user optimization is to achieve Pareto improvement. So how do we achieve Pareto improving? It's for users with losses. If you it depends, of course, on the willingness to pay, but if your willingness to pay is not greater than the price, then you're not a winner. And so users with losses, we distributed dividends or credits to each user that such that they bring them back. We can calculate the loss because we know their utility, their money metric utility, and we can see how much we need to compensate them in order to make them at least bring them back to the previous situation. But if we have extra revenue, we can even try to maximize welfare. The welfare is just a sum of these money metric utilities, so we can see where is the marginal utility of this dividend greater and offer it to people who have greater marginal utility. And hybrid is a combination of the two. So that's the idea. The idea is we have more revenue than we have the sum of the losses. We can, by personalized distribution, we can eliminate all the losers and maybe make people even greater winners. And so I'll show you now results of the simulation. And the results of the simulation are 6 strategies or 6 solutions, just pure pricing, no dividend, no cap and trade, and then uniform dividends. So that's another option. Another option is pricing with personalized social welfare maximizing dividends, and personalized hybrid dividends, meaning eliminate the losers, and then tradable mobility credit with uniform credit, everybody gets the same, or tradable mobility credit with personalized allocation of credit. So 6 different ways in which we can perform the pricing, and we can calculate, and we also change the network, we change capacity, also experimented with different level of heterogeneity and income effect. And the results are, this slide shows that the revenue exceed the losses. So there is sufficient, in all the experiments that we have done, there is always sufficient revenue, total revenue, pricing revenue to cover the losses. And so basically we show that in terms of social welfare, this is all congestion pricing scheme. simple pricing or pricing with revenue, the total social welfare, very, very little among these different methods. And, so the key difference between all these different ways of refunding or cap and trade is what will be more acceptable to the users. So the only thing that we achieve here is not, there is a little extra social welfare, but it doesn't seem to be significant. The key difference is making it acceptable. And this shows that these are cumulative, these here are the cumulative distribution. This is like the CDF of the social surplus at the level of the individual. So if it is monotonically increasing, it means that there are no losers. And if it goes down and then goes up, then it means eventually that there are some losers and then there are winners. So while they get to the same point eventually, in total, this idea of refunding and so the pricing with this hybrid method of distributing, the refunding the toll revenue, and the same idea applied to cap and trade leads to a situation when there are no losers. So that's the idea of pricing. The third idea, the third solution, is called here AMOD, but that's about technology. So the idea of the technology here is automation. When I was a graduate student many years ago in transportation, I was a graduate student more than 5 minutes ago, more than 50 years ago. And the idea of the best public transportation service was to be a taxi service that costs the same as a bus, so the same as public transportation. If we can provide kind of taxi service to people that are willing to pay what they now pay for public transportation, that was ideal. Well, at that time, the technology was not here, was not available. But now, the idea of robo-taxi, when you have no driver, the people have been calculating what the cost of providing such service and concluding that it may be even cheaper than providing mass transit with buses and subways and so on. So that's what we set out to study here. What will happen if we can provide such a taxi service, no driver, driverless, and the price that we calculated was that if we look at Uber type of service, this is pre-pandemic, it was approximately 20-30% less than taxi at that time, regular taxi. And people calculated that driverless taxi service, the cost can go down by about 50% relative to, so it's about, the idea was that it is about robo-taxi, taxi service, you can even share it, but the price for a trip would be about 1/3 the regular price by taxi at that time. So that's what we did. We've done simulations. So we use a laboratory, and the fleet size was determined to provide such a service such that people do not need to wait. Once they request a call, they don't need to wait, except for unusual situation, more than 5 minutes. So, but in order to study what will be the effect, what we did first was we wanted to have a global answer, not just what it is in Boston or what it is in Strasbourg, but if you look at all type of urban area, so we collected data on more than 300 metropolitan area worldwide. We classify them into 12 categories, and for North America, we came up with this. So these type of urban area, auto-sprawl, auto-innovative, and mass traveling heavyweight cover the urban areas in North America. Mass transit heavyweight, there is only one, but like Boston is auto-innovative, Houston, for example, is auto-sprawl. And then we conducted a detailed simulation. So the simulation have population, have agent, have network, there's cars that are moving on a network. These are all micro-simulation. So we've done it for these three typical prototypical cities that represent the situation in North America. And we analyzed three scenarios. One scenario is no robotaxi, just the existing modes. The other scenario, let's make these AMOD available, design the fleet. The fleet that is offered will be as needed, and the service will cost 1/3 what taxi costs pre-pandemic approximately. So this was a scenario which is called the AMOD introduction. And then we realized that there were a lot of counterproductive. There was too much congestion. There was too much cannibalization of transit. It was counterproductive. So if you are looking for emission savings or reducing congestion or any kind of objective, social objective of the kind, it was counterproductive. So we came up with another scenario which is called AMOD, transit integration, in which the service was regulated. It was regulated basically to support public transportation, and then the outcomes were positive, so that the technology was beneficial. So to conclude, AMOD introduction is determinantal to in all prototype studies. So unregulated kind of robotaxi allow them to roam the city and provide this kind of inexpensive transit is nice, but it's counterproductive. Integration reverses transit cannibalization and also emission, and so it needs to be regulated. That's the conclusion. So my area of expertise are choice models of different kind, and also integration of choice model and other kind of econometric methods. And so we have a very complicated behavioral models behind this simulation. And and they predict human factor in response to the kind of solution that we are interested in analyzing. In addition, I hope I convince you this smart analytics, the tripop idea, facilitate the development of attractive solutions. And I showed you three examples where we actually apply this idea of designing the solution to be productive. Thank you.
Thank you for the great presentation. I'm here. Just a technical question in your model. When a new customer penetrates your application, how is it going with the first iteration, and how much of historical data you have to apply the behavioral model to this new customer?
The modeling technology behind is Bayesian updating. So there is a prior, there's a model that's developed a prior. So if a customer comes for the first time, the recommendations or the personalization is based on a prior distribution of preferences. And then it gets updated as when an individual comes back to the system and make a choice, then the preferences are updating. So there is the data handling in these behavioral models is such that whatever data you conduct surveys, use whatever surveys you can find, you develop models that then serve, from which you can get a prior distribution for every person that you keep updating.
Well, thank you for the presentation. So correct me if I'm wrong, the system you developed seems to rest on your ability to conduct, at the end of the day, perfect price discrimination, right? So you're learning about the preferences of those people, and you know the welfare gains and the losses of each individual. So if this is true, that requires a lot of data, behavioral data on people, which they usually don't like to share. And second, firms doing those kind of things, this is something that usually people don't like for moral reasons. So do you think that practically speaking, this is something you can deploy at a massive scale?
Well, it achieves perfect price discrimination, but by refunding, right? So the refunding is individual specific, and it depends on their willingness to pay, but it's not exactly their willingness to pay. So it's not perfect price discrimination. The price is the same for everyone at a given point in time. For a given location, the prices are the same. There is no difference in prices. Everybody sees the same price. The refunding is different. So now the question is, can with mobile devices and everyone communicate with the system, can you achieve price discrimination? Probably. The way we have done it in terms of is not price discrimination, but discounting.
Maybe let me reformulate my question. Did you investigate how people feel about those refunds, which basically tells them that you know something about them, you know something about their surplus, which places them somewhere in the social distribution, right? So did you get data on how people feel about that? That's my worry.
I know how I feel when I get a refund. It's no, we don't know how people feel. But in terms of privacy, there are all kinds of issues of privacy here. Clearly, when you subscribe to the system to be able to receive the refund, you are agreeing to give up some of your privacy. So you don't have to subscribe. It's optional. If you want to get a uniform treatment or no refund, then you don't have to disclose anything about yourself. So it's a trade. You give up your privacy in return for some monetary gain. And I started to answer questions that you did not ask, which was about price discrimination. So we are working, this is my group, my research group, we are working on what in the US is called managed lanes. Managed lanes, I don't know if they exist in Europe, but basically you have a highway, and then in the median, between the two directions, you have lanes which sometimes are referred to as Lexus lane. You pay to use it, and the toll fluctuates to make sure that these Lexus lanes are never congested. So you have the freeway, which is free, and you don't have to pay a toll, but you can use these lanes, and then you have to pay a toll, and the toll fluctuates. So we have used exactly the same idea to offer discounts. So the company it's a private business. They offer discounts because there are people that are price elastic. And so if you're price elastic, you'll get a discount. And how people are, we didn't ask people if you are happy to get a discount. We assume they will. Yeah. They don't need to subscribe, then they don't get any discounts.
Yeah. Rob Lindsay, UBC. As you know, New York City spent years developing a congestion pricing scheme, and it was set to start shortly. And then the governor turned it down. And my question, which is perhaps a bit of a tough one, is could you have designed a modified pricing scheme so that the governor would not have canceled it?
I'm afraid to answer this question because I will reveal the way I feel about it, which is not very well. They tried. Actually, they spent many years, like you said, designing the scheme, and there was a discounting, a low-income discount. The major refunding, it was totally refunding. The entire total revenue was dedicated to improvement to public transportation. So the people using public transportation, which is, a significant share of the commuters, people that come in and out of the tolling area, would have benefited. Plus, there wasn't like some sort of an income discount, low income discount. So there was a system. There was in place some sort of refunding. Could they have designed it better? Of course. I mean.
I have a last question to ask, because we are ending up. When you talk about data collection, especially in the case of human, it's quite difficult to collect, first of all. Second, the behavior of every person is different. Third, is also the data collected from a human is not to be very precise. They just give you the data, survey, the response to survey, without thinking. They just answer okay, I like it, I don't like it, or rate it 8 or 9, random, just. So how reliable these data are when you plan something your policies according to these particular data, comparing to the data just coming from technical fields or coming from the human fields. So there's quite difference between that.
The data that we use mostly comes from electronic means of collecting data. There are a lot of sensors nowadays that collect data in a transportation network. And there are, of course, data that comes out of smartphones. And so that's any kind of big data that comes up from people using smartphones that this kind of data are available. In addition, we conduct surveys. My lab developed a software that has been since commercialized to conduct surveys using smartphone, relying on all the sensors that are available in the smartphone and machine learning methods that allow us to interpret the readings from these sensors. So we make inference about people's activity, modes, where they go, when they go. So we have a lot of good data. So it is not based on people's subjective responses to, how satisfied are you with your life today? No, okay. That's not the kind of data that we use. Although this data could be useful, but that's not the data that we use to estimate the models.
But you are taking the subjective data also in the form of surveys. And second thing is, when you're saying you're accessing the data from the mobiles of the different people, you have a concern before you take that data? It's like a data privacy thing.
The data from many of us is continuously being collected from this smartphone, either by the telephone company or by the different apps. And people often are consenting, giving a consent to the app to collect their data. So it's, in addition, there are other data that is passively collected that you can use data which is more selective to calibrate it. So there is plenty of data. But if there are surveys in which people are asked subjective questions, there are methods to analyze such data and combine discrete choice model. These are called latent variable methods. So the combination of the two, we refer to it as hybrid choice models. So that's the way we would analyze objective or measured choice data with subjective response to a survey questions.
Thank you, Professor.